In this video, we quickly remind you of what a vector is. For the purpose of this course, a vector is a one-dimensional array of n numbers, where n is finite. The numbers will be referred to as the components or elements of the vector. In this example, we denote the vector by the symbol x. We will always think of a vector as being a column of numbers. The components are ordered, so it is not a set. We will use the Greek letter chi to denote the components of vector x. In general, we will use Greek letters to denote scalars and lowercase letters to denote vectors. We will choose a Greek letter that resembles the lowercase letter used for the vector to denote the scalars that are components of the given vector. So, chi is a Greek letter that is similar to the Roman letter x. Chi sub I is the ith component of x. Or, since we start indexing at 0, perhaps we should say chi sub I is the component of x indexed by I. We are computer scientists, so we start indexing at 0. But the programming language we will often use starts indexing at 1. This is the Mscript language used by the MATLAB environment and the open source version of MATLAB called Octave. The LabVIEW scripting language called MathScript is also very similar to Mscript. Each number in the vector is a real number. We can denote this by indicating that chi sub I is an element of R, the set of all real numbers. For most of the course, we will restrict ourselves to the real numbers. Most of the insights and theory carries over to the case where complex numbers are involved, but we will avoid those until we discuss eigenvalue problems. To indicate that the vector x is a vector of size n with real valued components, we will say that x is in the set Rn, which is the set of all vectors with n components. A vector written down looks like an n-tuple that denotes a point in m-dimensional space, with the coordinates of that point written as a column of numbers. However, it has a direction and a length. But, importantly, it does not have a location. Let us look at an example in 2 dimensions. Here are the customary coordinate axes. Let's call them the x-axis and the y-axis. We can place a point in the plane, say the point 4, -3. A vector can then point from the origin to that point. However, the vector does not have a physical location. It is sometimes convenient to draw it so that it starts at the origin, but a vector that points in the same direction but elsewhere in the plane is still the same vector. All the illustrated vectors are one and the same. They have the same direction and the same length. Indeed, we can simply remove the coordinate axes and we are still left with the same vector. This vector points 4 units to the right and 3 units down. Its length is the Euclidean length of the vector, the square root of the sum of the squares of the sides, when viewed as forming a right triangle. Its components, also referred to as its elements, are 4, -3. This example in 2D generalizes in the obvious way to higher dimensions.